tens of thousands of miles, the total distance covered by the National Railway Network. Behind this infrastructure lies an advanced track-laying operation where every rail, weighing hundreds of kilograms, is positioned by domestic automated machinery. But this is just the beginning. Why rely on these massive yellow giants? At first glance, placing tracks seems like a standard construction task, but in reality, it demands micron precision. The equipment aligns every segment to ensure the system handles extreme loads without deviation. One can notice how the machines lift, align, and weld the joints into seamless ribbons of steel. They crawl forward, leaving behind a continuous structure that stretches beyond the horizon. The steel path expands steadily across the land. 350 kilometers per hour is the speed dividing two engineering eras. In the United States, most lines are still built using the traditional method with layers of crushed stone known as ballast. At first glance, this seems simple, but in reality, it distributes weight and keeps the track structure stable. The stones also allow rainwater to drain away from the track bed. China, on the other hand, has taken a completely different path. On next-generation high-speed railways, the stone is replaced by a continuous concrete foundation known as slab track. Why fix rails directly onto the concrete surface? The answer lies in stability. Fully automated machinery installs the track with zero deviation. One can notice how laser systems align everything into one unified body. The structure becomes stronger, more durable, and incredibly precise. But this is just the beginning. As a result, Chinese trains can travel smoothly at speeds exceeding 350 kilometers per hour, 2 to 4 feet. Typically, this is the depth of the firm foundation achieved by grading and compacting multiple layers of soil and gravel. This thickness depends strictly on the terrain and the expected train loads, creating a stable subgrade that will support thousands of miles of railway. Once the base is stable, engineers begin spreading the ballast, but the approach here changes drastically. Why is this stone layer left loose unlike the solid concrete of the subgrade below? At first glance, bonding the stones together would seem to create a stronger structure, but in reality, the layer must remain loose to effectively absorb vibration and allow rainwater to drain freely through the track bed. 1 mile of track requires nearly 3,500 tons of ballast, which amounts to around 7 million pounds of stone. One can notice how the material is released from specialized hopper cars, forming rough piles that require immediate attention. A ballast regulator, a machine fitted with plow blades, rotating brushes, and laser-guided leveling boxes, enters the scene to distribute the stone. Modern versions produced by manufacturers such as Placer and Thurer can operate with minimal human input, automatically adjusting height and slope within minutes. After distribution, powerful vibratory compactors press the ballast into place, creating a dense and perfectly stable foundation. Completing just 0.6 of a mile of track can take anywhere from several hours to a few days, depending on soil conditions and site terrain. But this is just the beginning. After the ballast layer has been evenly distributed and roughly leveled, construction crews move on to positioning the sleepers, the foundation pieces that define and lock in the exact alignment of the entire railway track. In most modern railway projects, this process is performed by an automatic sleeper laying machine that moves with robotic consistency. Using powerful hydraulic clamps, the machine lifts each sleeper, weighing between 600 and 700 pounds, and places it precisely according to its marked position. Each sleeper is spaced about 2 feet apart, and during a single shift, the machine can install more than 2,000 sleepers with remarkable accuracy. Sleepers can be manufactured from several materials, and the choice determines the longevity of the line. Traditional ones are made of wood, pressure, treated with creosote oil to prevent rot and reduce vibration. However, their lifespan is limited to around 20 to 30 years. Today, reinforced concrete sleepers have become the industry standard. They are heavier, stronger, and capable of lasting over 50 years while supporting much greater loads. For maintenance or track renewal projects, engineers often use panel track systems, comprising pre-assembled rail and sleeper sections built in factories. Once thousands of sleepers have been positioned with precision along the prepared route, the next stage begins: rail laying. Each steel rail, typically 78 to 80 feet long and weighing around 1,300 pounds, is delivered to the site on specialized transport vehicles known as rail trains. In modern railway construction, engineers often rely on continuous welded rails, or CWR. These are long steel segments pre-welded at the factory, each stretching up to 1/4 mile in length. At the work site, the rail train gradually feeds these immense steel ribbons from the rear. Simultaneously, hydraulic winches pull them forward and align them along the track bed. It is visible how workers guide the rails to glide smoothly over the ballast, positioning them perfectly atop each sleeper and holding them in place with temporary steel clips or pins. Once alignment is confirmed, the rail tensioning phase begins. Each rail is stretched or anchored using hydraulic tensioning machines to account for thermal expansion and contraction. This is a vital step that prevents future warping or buckling under the sun. After the rails have been perfectly aligned in place, the next step is to install the rail fastening system. This network of smaller components keeps the entire track secure and stable. Each fastening assembly is made up of a steel base plate, rubber pad, spring clips, and anchor bolts. The base plate evenly distributes the wheel load from passing trains across the sleeper. Meanwhile, the rubber pad beneath it cushions vibration and helps reduce noise. Workers move steadily along the track, fitting each set of fasteners into position. They tighten the bolts with Torx wrenches to the precise specification, ensuring every joint applies the same uniform pressure. Once the bolts are secure, the clips are locked into place. They hold the rail firmly against the base plate, while still allowing slight flexibility for thermal expansion and contraction as the steel responds to temperature changes. Everything only gets more complicated. Once the entire fastening system has been installed, engineers move on to the stage of track alignment and ballast tamping, a precision process that determines how smoothly a train will glide over the rails. A specialized tamping machine travels slowly along the track at an average speed of 0.3 to 0.5 miles per hour, equipped with dozens of hydraulic vibrating tines. During operation, the machine lifts the entire rail sleeper assembly by about 1 to 2 inches. At the same time, the vibrating tines compact the ballast beneath at a rate of roughly 35 to 40 vibrations per second. This synchronized motion locks the crushed stones tightly together, creating a dense yet flexible foundation capable of absorbing impact and maintaining long-term track stability. Meanwhile, laser sensors and gyroscopes continuously measure elevation, tilt, turn, and alignment. Any deviation, even as small as 1/10 of an inch, is instantly detected, and the system automatically corrects it to match design standards. With this level of automation, a 1-mile section of track can be fully aligned and tamped in just 2 to 3 hours. This makes the process more than 10 times faster than traditional manual methods. Once the entire track has been precisely aligned, engineers proceed to the rail welding phase. Two main techniques are typically employed: flash butt welding and aluminothermic welding. In flash butt welding, the two rail ends are clamped tightly together by an electric welding machine. A powerful current passes through the joint, heating the steel to nearly 2,700 degrees Fahrenheit until it softens, melts, and fuses into a single continuous rail. In more confined or remote areas where access is limited, engineers rely on aluminothermic welding instead. In this process, a mixture of aluminum powder and iron oxide is ignited inside a cast iron mold. This triggers an exothermic reaction that can reach temperatures of up to 400 to 500 degrees Fahrenheit, according to the reading, hot enough to liquefy steel and fill the gap between the rail ends. Once the molten metal cools and solidifies, the excess material is trimmed off. The joint is then polished using a rail grinder, removing any ridges or surface irregularities to ensure a perfectly smooth and seamless running surface. Once the entire rail line has been welded and ground smooth, the final inspection begins. Engineers use an ultrasonic flaw detector to scan the rails, detecting microscopic cracks or internal voids hidden deep within the steel, flaws invisible to the naked eye. A track geometry car then measures elevation, tilt, curvature, and gauge width with precision down to 0.02 of an inch. Any deviation beyond tolerance is corrected immediately using tamping and alignment machines. When all readings meet the standard, a test train is deployed to assess ride smoothness and vibration. It accelerates from 30 to 80 miles per hour, while hundreds of sensors record load and oscillation data. If the results fall within design limits, the railway is certified for operation, ready to carry its first train with precision and stability. 2,900 degrees Fahrenheit is the temperature generated inside the massive electric arc and blast furnaces, where the production of railway rails originates. Here, raw iron ore, coke, and specific additives are transformed into a uniform molten stream capable of eventually carrying thousands of tons of load. An automated feeding system measures every batch of ingredients down to the pound to ensure absolute consistency in the mix. Spectrometers and thermal sensors continuously monitor the chemical composition to detect even the slightest deviation in the liquid metal. One can notice how heat-resistant robots stir the blindingly bright melt to mechanically remove impurities floating on the surface. But this is just the beginning. Why introduce alloying elements like manganese and chromium into the mixture at such a late stage? The molten steel seems fully prepared for casting. These additives are strictly necessary to enhance the rail's strength and its resistance to wear under the constant weight of railway traffic. Once the desired composition is achieved, the molten steel pours into molds to form solid billets, which then transfer directly into soaking pits. Inside these heating chambers, an automatically controlled combustion system maintains the environment between 2,200 and 2,300 degrees Fahrenheit. This heat stabilizes the internal structure of the metal before mechanical processing begins. At first glance, this heating stage seems like a simple pause in production, but in reality, any sudden drop in temperature could cause surface cracking or deformation during the subsequent rolling. Infrared sensors monitor every point on the billet surface to ensure it does not cool too quickly before entering the line. From here, massive heat-resistant rollers on the preparation line begin stretching and flattening the material with immense force. High-power hydraulic motors and gearboxes regulate the pressure, while an electronic control center gathers data from dozens of sensors to fine-tune speed and force in real time. The process is only gaining momentum. The glowing red steel billets enter the continuous rolling line where the shape begins to change. Because the signature eye-shaped cross-section requires gradual sculpting, the process starts with a roughing mill, where large-diameter alloy steel rollers apply pressure to reduce thickness. Intermediate stands use staggered rollers to both press and rotate the billet, distributing stress evenly to prevent structural failure. One can notice how high-pressure water jets blast the surface between stages to remove oxide scales that form on the hot metal. The finishing stand eventually shapes the profile down to the millimeter, creating a thick head for load bearing, a slender web, and a broad base. And this is not the limit. Laser sensors continuously measure width, straightness, and contour, sending real-time feedback to the control center, which adjusts the roller gap during operation. A standout feature of these modern mills is the quick change roller system, which allows different profiles to be produced without halting the line. This ensures efficiency in high-output plants. As the rails exit the rolling section, they immediately pass through a high-pressure water spray system while still glowing hot. A dense mist envelops the entire surface as the computer controls flow rate and spray speed to ensure uniform cooling and prevent warping. Next, the rails enter the heat treatment zone, operating between 900 and 1,100 degrees Fahrenheit, depending on the required mechanical properties. This combination of rapid cooling and annealing improves fatigue resistance and preserves the I-beam profile. Transition to the next level. Therefore, each rail can endure millions of loading cycles without deformation or structural failure. It is visible how the welding line joins individual rails into seamless tracks, stretching hundreds of feet in length. A system of guide rollers aligns the ends with a precision within 1/100th of an inch. Flash butt welding technology uses a powerful electric current to heat the ends to over 2,700 degrees Fahrenheit. The metal fuses into a single solid piece under pressure, after which an automatic grinding machine removes excess metal for a smooth joint. Everything only gets more complicated. The central control panel records key parameters such as temperature, pressure, and timing to ensure the weld matches the integrity of solid steel. Finished rails transfer to the automated inspection area where high-speed cameras scan the surface at microscopic resolution. Meanwhile, ultrasonic and X-ray systems examine the internal structure to detect hidden defects. Random samples undergo testing in tensile machines, compression rigs, and Rockwell hardness testers to evaluate load-bearing capacity and deformation resistance. Any rail failing to meet specifications is automatically rejected by the system to prevent it from reaching the tracks. Each unit that passes is laser marked with a traceable identification code to ensure production transparency and consistent quality. The finished product is now ready for shipment. Two parallel steel rails have fused into a single durable line. Why is the construction process considered fully complete? The heavy equipment leaves the site. It is complete because the railway track is finally ready for operational loads. At first glance, the rails seem static, but in reality, they are ready to flex under thousands of tons. One can notice how the perfect geometric alignment stretches toward the horizon. But this is just the beginning of the infrastructure's life. The engineering cycle of building the track is finished. New technical narratives from Mandarin Tech await ahead.